what is the gravitational constant G? Well, we're talking about not the mathematics of it. We're really not interested in the mathematics. We're not going to do problems here, put numbers in there, and try to calculate something. We're trying to figure out what is the meaning of the equation. What does it represent? Okay, especially in physical terms. Here we do physics. We don't do math. Okay, but we're going to analyze the variables that are included in that value, and also in the equations that we're going to look at here, especially Newton against Einstein. So here we had the two champions. One is Newton on the left and Einstein on the right, and they both use G, gravitational constant G, in their respective equations. Okay, and so let's look at this. What does G mean? I mean, why did they put that in there? What is the physical significance of that letter G? Okay, and we start with this. We're showing that this is what the issue is, or at least probably the main issue. Okay, and that is you have the sun and the earth, and the question that everybody wants answered is, why doesn't the earth spontaneously fly away from the sun? Okay. Why? I mean, what's holding it to the sun? Why does it keep rolling around in circles around the sun? And that's going to relate to this gravitational constant G, okay? And we'll look at the different equations here. Here's Newton's equation, okay? And he says, well, it's mass divided by distance squared. The R stands for radius squared, okay? Because it's to the center of whatever spherical object you're referring to. In this case, you have the distance really from the center of the earth to the center of the sun, but irrelevant really to some degree. What we're saying is you have mass, distance, and why put the letter G? Why did Newton put the letter G in there? Well, it turns out he didn't, and in fact, he doesn't have a single equation in his famous book, Principia, okay? What he has is an explanation, and there's a reason for that. And the reason is he had no values for the mass of the sun, the mass of the earth, the mass of the moon, okay, the things that he talked about. So he had no values, and so there was no reason for him to put really an equation. He explained it qualitatively, right? Which is the way physics should be done, okay? But what was important is that, and here you see his notion of how he pictured this, what was going through his mind. He said, look, you have these particles because, they all believed in the ether. And what is the ether? The ether is a bunch of particles. And etherists don't understand it even to this day. But yeah, that's what the ether is, a bunch of particles. And the only difference between Newton and the wave folks, such as Huygens and Robert Hooke, was that these other fellows said the ether waved up and down, whereas Newton said it goes straight. Okay, that was the difference between them. But they all believed in the ether. What was the ether? A bunch of particles. Okay, but then he could not explain with this how, the earth was physically tied to the sun. He could not explain it. In fact, he says the following, okay, this is a famous quote from him in a letter to Bentley. Okay, he says, it's conceivably that inanimate brute matter should, without the mediation of something else which is not material, right, operate upon and affect other matter without mutual contact. That one body may act upon another at a distance through a vacuum without the mediation of anything else by and through which their action or force be conveyed from one to another is to me so great an absurdity that no man can fall into it, he say, and gravity must be caused by an agent acting constantly. And so he could not explain it with his particles because he was thinking of particles. And that's one of the problems that eventually spelt his doom. Okay, because he was thinking in terms of particles, but when we get to the 20th century, they said, well, we cannot explain it with particles, especially particles coming one way. I mean, the only way a discrete particle can fly or travel is in a single direction. How do you pull on a donkey by throwing stones at it? Well, you can't. And that was the problem he had. He had no mechanism to explain gravity. Oh, he said, look, I've got the equation, mass divided distance squared. That he could understand, but he could not understand the physical mechanism. Okay, so up comes Einstein, 1915, he writes his general relativity equation. What was the important thing about that? The important thing is that he introduces the field, the notion of a field, into gravity. And he's saying, look, it's a field equation. And what is a field? Well, a field is really a bunch of numbers. That's all a field is, a value at each point in space. It doesn't matter how close one point is to another. Each one has a distinct value of gravity, gravitational value. But what is the sense, the physical sense of that? Well, the physical sense is a field is thought of as a continuous sheet, canvas, fishnet, right? We have a continuous sheet, bendable, right? And so suddenly, instead of particles flying from the sun to the earth or vice versa, or both ways, right? What we have is a platform. There's a trampoline, there's a canvas, a fishnet underneath both bodies, and they weigh it down, and so it's continuous. And now gravity is going to propagate along this so-called field. Okay, that's the notion these people had. Okay, and so here it is. Okay, this is Einstein's original equation up there, more or less. It's a different version of it, but it doesn't matter. They're all the same, really. And it says, relate space-time curvature to the stress energy of a system. Well, we have a problem because, what do you mean the curvature of space? And what do you mean the curvature of time? What does that mean? How do you curve time? So the physical interpretation is totally irrational. All you can do is talk about mathematics, and this is more or less a way of presenting mathematics in some way that you can relate it to physics. But it ain't, because the whole notion of what they're talking about, curvature of time, doesn't make any sense whatsoever. So you cannot turn your math into physics just by using these fancy words. Okay, that's the issue. Then you have, others. One is the amount of energy, or the fabric of space. What do you mean the fabric of space? Space is not a fabric. Space is nothing. So to say the fabric of space is an irrational statement because it doesn't match, the real world. Amount of energy, well, what is energy? Well, to this day, as I've shown before, nobody's defined the word energy. No one knows what an energy is. Richard Feynman, Nobel Prize of 1965, famously said, we have no idea what energy is. Yeah. Then you have another one, properties of every point within space-time. You have another variable there, product of constants. And the last one, energy, momentum, and stress. That's what that equation's talking about. What are they talking about in the last one there? They're talking about really this notion they have of dark energy, okay? And which Einstein said was his biggest blunder because he wasn't able to make sense of it when he wrote his equation for the first time. What is dark energy? Well, it's that thingy, that ocean, that medium that is pushing everything apart since the days of the Big Bang, 13.8 billion years ago. So you have this expansion of space-time, right? And it's all being pushed by this physical entity they call dark energy, when energy is a concept, an undefined concept. Nobody knows what energy is, but that's what they use. It's like saying X. And you say, well, what do you mean by X? We don't know what we mean by X, but that's what's pushing everything out. It's whatever's pushing everything out, that's what we call X. That's what they call dark energy. Okay, so talked about a tensor there. What is a tensor? Just so people know here. In general relativity, the presence of mass and energy causes space, what? Time to curve. They cause time to curve. How do you curve time? This curvature is described, not explained, but described by the metric tensor. So you're talking about a quantitative analysis of something, and they're going to describe it, and they're not going to explain what it is because they have no clue, okay? Which encodes information about how distances and angles change in curved time again. We have curved time all over the place. They're curving time, they're bending time, okay? And there you have the tensor at the bottom, gives you an idea, okay? It's just a more sophisticated matrix, that's all it is, Okay, so you see the matrix here, just 1, 2, 3, 4, and what's a tensor? Well, it's a more sophisticated one where you have 1, 2 on the one in one block, 3, 2 on the other, 1, 7, 5, 4. That's called a tensor. So it's just a more complex matrix. That's all it is. And it says their tensors are coordinate independent mathematical what? Objects? What do you mean objects? What's an object? This means that the equations and relationships involving tensors hold true regardless of the coordinate system chosen to describe space-time. And vectors, on the other hand, are coordinate dependent. Okay, so that's essentially the difference between a matrix and between a vector and a tensor. Okay, so we don't care about all that gibberish, okay, because we're interested in physical interpretation. We're doing physics here, not math, okay? And so what's the bottom line? Well, this is what they came up with. They said, look, here's the sun and here's the earth, okay? And what we have really here is that the earth doesn't fly away because there's this canvas, this field, this continuous entity, this continuous ocean, so to speak. And when the sun weighs it down, it curves it. You're curving time there because those white lines that you see there, that fishnet, it's space-time. We don't know what the black stuff is because that can't be space. Space-time is the net. So keep that in mind. But anyways, the sun weighs down the space-time canvas, and that prevents the Earth from flying out of the solar system. Okay, so what is Einstein saying essentially, or his followers today? Essentially, it's a roulette system, okay, very easy to understand. You have the sun there, and it creates this warped region around it, and the Earth doesn't have any choice but to go around because it encounters a wall of warped space-time that prevents the Earth from leaving the solar system. Of course, when you point that out to the mathematicians, they say, well, you're taking the analogy too literally, and et cetera, et cetera. It's just philosophy. We don't care about that. We care about the math. If they only care about the math, why don't you stick to math and forget about physics? Forget about giving a physical interpretation to something that you don't understand and that you cannot explain. Because they give these physical interpretations when you point to them that it's irrational. They say, oh, you're taking it too literally, and that's philosophy anyways. So why are you doing philosophy if it's not your job? It's not in your job description. It's not your field of work. That's the issue. They should be doing physical interpretations, and they have no idea what they're talking about. Okay, especially if they talk about warp time. What the hell is that? Okay, so here we have Mr. Wheeler, and he synthesizes for us Einstein's equation, which includes the gravitational constant G, by the way, and says, space-time tells matter how to move, matter tells space-time how to curve. That's in a nutshell what Einstein's equation means from a physical point of view, except that, they say, time essentially tells matter how to move. No, time cannot tell matter how to move, and matter cannot do anything to time, especially curve it. So it's the physical interpretation which is irrational. So whatever they come up with, these syntheses, doesn't explain anything. It doesn't tell us anything about what's going on in the physical world, in the real world, okay, out there. That's the issue. And so these people are kidding themselves when they say that these are the physical interpretations, and more so when they actually, a lot of them believe them. They say, yeah, it actually warps. And they'll tell you that we've proven it warps because otherwise GPS wouldn't work and blah, blah, blah. A lot of stuff like that. Nonsense. This is more or less what Einstein was saying. He's saying, when you take a step, he did it with Mercury. And he says, look, we're different than Newton, not only in the fact that Newton just has these particles going from the sun to the earth, somehow keeping it faithful to the sun. He did it with Mercury, but that's one issue. But the other issue is that Einstein, his equation, because it's a field equation, he says every step that Mercury takes, it also bends space-time. And the sun is also going around the Milky Way, so it's also bending another space-time. And so what happens? This mutual interaction causes the canvas to change its shape, okay? And here I'll show you a simulation of that so you can see what I'm talking about. You have these kids, and you can see when they take a step, it bends the trampoline. And that causes them to take a different kind of step than they would if that thing was, solid, straight, without bending. But by bending, their next move is going to be different, and it's different for all the other kids. In other words, all the other planets, right? You move the canvas, and it changes the canvas, the shape of the canvas, and that forces you to move in a different way and other things to move in a different way as well. And that's more or less the notion that Einstein had for his field equation. He says, look, Mercury is bending space-time, and that's going to cause the next motion of Mercury to be different, especially when the sun does exactly the same thing. Okay, so everything is dynamic. And the mathematicians eventually liked that because they liked that they could explain that a little better, with the field notion than with Newton's particles. And that's force, And so they dropped the particles, the force, and they said, no, we're going to go with space-time. We think that's a better physical interpretation that we can relate to, and we have the math to support it, which they said is a little more accurate than Newton's. And in fact, Einstein's equation said to approach Newton's at the limit. And you can see why, because Einstein's is a dynamic equation, whereas Newton's is a static equation. You're not talking about distance traveled in the case of Newton's equation. You're talking about the distance of physics, separation. So it's a static notion. And when you take Einstein's moving or dynamic equation, at the limit, at location, it matches Newton's. No kidding. Yeah, it's got to. Because motion, the limit of motion is location. Okay, in physics, okay, in rational physics. In math, they say, well, we take the limit and we approach Newton's equation. Okay, whatever. Anyways, here we have, start with Newton's again, see if we can find out what this gravitational constant G is, okay? And Newton did not put it in there. In fact, he was not able to calculate it again because he didn't have the masses of the sun, the earth, the moon, and any of the celestial objects in the solar system. So he just gave us the physical interpretation. In fact, the equation was solved by someone else. The gravitational constant G came in later when they started doing some measurements and calculations. They said, we're going to need this gravitational constant G. That's where we're getting at. And so here's where we start. We say, look, we have a man standing on the earth, okay? And so how's Newton going to calculate this? The gravity or the force of gravity, right? Why is there such and such acceleration? And this is more or less how Newton comes up with it. He says, look, and really this came after Newton, but we'll attribute it to Newton, okay? We have mass times mass divided by distance squared, and we have to multiply it times the gravitational constant G. But what if we took the G out? Okay, let's assume there was no G. What would we get in that case? And here you see the problem. You see that you would get the force of gravity is kilogram squared over meter squared. And what the hell does that mean? What is kilogram squared over meter squared? Well, what interpretation can you give to that? So what happened? They put the gravitational constant G. Why? Because it was put in there by hand. It was ad hoc. Okay, they had no idea. They just needed the units to put in there, and that's how this came about. You can see there if you put the gravitational constant G, which is meter cubed divided by kilogram second squared, if you put that in that force equation, well, you cancel out the meter cubed with a meter squared, leaving meter at the top, okay? And you cancel the kilogram squared at the top divided by kilogram at the bottom. That gives you kilogram at the top, and eventually second square at the bottom. And you end up with what is known as the Newton, which is the unit of force, okay? Still makes very little sense because they say, well, it's 1 kilogram per meter per second per second. That's what a Newton is, okay? Whatever that means to you, okay? But that's the notion they had, but they had to put in these values by hand. Okay, and yeah, based on that, you're able to calculate, not only the force of gravity, especially here on Earth, you can calculate the acceleration of gravity, these sort of things. But that's great. But what does G mean? I mean, what is that strange unit, that weird unit that he just put in there? And so we go to the experts. Okay, when we try to answer these sophisticated questions, you have to go to the experts. So we have here the PhDs on the Stack Exchange, and they tell you exactly what it means in physical terms. So someone asks the question, what is the physical meaning and origin of the gravitational constant G? And here's the answer. It says, it is just a value to fix the units in the equation. So it was put in there by hand. Okay? There is no physical content to its value other than to describe the size of the unit of mass compared to the units of length and time. So it was put in there by hand. These people had to put these units in there so that the equation came out right. What does it represent in general relativity theory? Well, the answer is simply a unit of conversion. Usually we simply get rid of it by using units such as c, velocity of light squared, velocity of light, right, equals gravitational constant equal 1. And does it have any physical meaning or physical origin? No, or rather no physical meaning beyond the choice of units. Okay, so there's your answer. What does the gravitational constant G mean in mathematical physics and general relativity? Means absolutely nothing. They have no idea what it means. They just put the units because it helps them calculate. But they have no way of relating that to the physical world. That's the issue. Okay. Okay, so here we start with our version of it. Y is mass divided by distance squared. Here it is, okay? This is what it looks like. Every atom of that man's body, we're just going to take only one atom at the end of his toe, okay? And it's connected to every atom on Earth through electromagnetic ropes, which is the mediator of gravity and of light. And every atom in the universe is connected to all others. So we have one atom there connected to every atom on Earth. And of course, I did not draw all the atoms, but you can appreciate what's happening here. As an astronaut falls to Earth, the ropes widen out, they fan out. And so his acceleration is greater as he falls. There is an acceleration of gravity. And you can see why, because as he approaches the Earth, the distance becomes less and less, and it decreases, then the guy is pulled at a faster and faster rate. Okay, so that's our explanation. But we still haven't explained, the gravitational constant G. All we're explaining is mass divided by distance squared. Okay, that's so let's keep that in mind. So we had this value, and it comes from Cavendish, and really good old Cavendish should not take the credit for it, for building his, maybe for building his torsion balance. The guy who came up with that was John Mitchell, but John Mitchell died 5 years before this fellow was able to publish his experiment, and that's how he came up with the value for the gravitational constant G. And this is what it looks like today. Okay, here you'll see it. Okay, you have two weights, and you let another pair of weights hanging from a little thing that connects them, and they're tied in by a little thread going to the ceiling. And you can see over time, one weight approaches the one closest to it, and the other one approaches the other. And it's this torsion on the string, on the thread that connects them. It's that torsion which is measured, okay? And this is essentially the force of gravity, because you can see that it's not a downward gravity, it's a sideways gravity. One mass is attracted to another mass, so to speak, which is, Newton's equation, okay? Mass, distance squared. And the closer they get, the faster they go, okay? You'll see that there. Of course, it's very difficult to measure because it's a crude experiment, but yeah, they go faster and faster and faster. Okay, so that's how they calculated the gravitational constant G. Okay, we have a value, and the units by hand, because they needed those units, okay, to make sure that the equation checks out okay. Okay, so here we have the gravitational constant G, and we have it there, 667. times 10 to the minus 11 newtons meter squared over kilogram squared. What in the world does all that mean? Well, the Newton is a kilogram meter over second squared, okay? And so when you look at that, it comes out to 667 divided by 10 to the 11th kilograms meter cubed over kilogram squared second squared. You cancel out kilograms there, and you end up with a unit of the Newton, which is meter, with a unit of gravitational constant G, which is meter cubed over kilogram second squared. And still, we have no idea what that means, okay? What does that unit represent? Because it's a single unit, meter cubed, kilogram second squared. What can that possibly mean? And one of the problems we have is that these people try to synthesize it and make it even as smaller or as synthetic as they can possibly get it. And here you see this is the end result of their work. Okay, and sometimes they make it even worse by saying, oh, it's so many newtons. Okay, instead of meter cubed, kilogram second squared, they put it in terms of newtons. And what they've done really is cloud themselves or blindside themselves to the problem. They blindsided themselves to the solution of what the gravitational constant G represents in physical terms. If they would have left it as it was, they probably would have figured it out. But they never will, because they synthesize and synthesize and synthesize to get it ever more efficient. And here we don't need efficiency. We need exactly the opposite. We need to know exactly, in a crude way, what these numbers, what these units represent. Okay, so here's the gravitational constant according to science, to physics, to the rope model. Okay, so we're going to put the numbers first, then we're going to justify them. Okay, so here we have it. We take that 667, 10, 11 meter cubed kilogram second squared, and we bring it to where you see number 1 there. Okay, that's the same value there, meter cubed over kilogram second squared. Okay, and then we go to number 2. We're going to multiply that value, the G, by 10 to the 16 kilogram over 10 to the 16 kilogram. In other words, we're going to multiply it times 1. So we've committed no crime. This is just straight mathematics. Okay, and now when we do the multiplication there, we end up with number 3 there, 667 times 10 to the 16 over 10 to the 27. And an impossible number, we don't even know what that's all about. But once we look at what it could represent, we find out that it does make sense. We find that 1.67 over 10 to the 27 is the mass of the hydrogen atom, which is the unit of mass that Mother Nature uses. That's the smallest unit of matter. There's nothing below that, because below that it's not called matter. Okay, under the rope model. Okay, and then you multiply it times the velocity of light squared, which ends up being 9 times 10 to the 16th there. And now, yes, we can eliminate 2 big factors. One is the mass of the hydrogen atom. The other one is the velocity of light squared. And we're going to multiply it times that remainder there, 0.44 meters over kilograms. We're not going to go over that one. Anyone who wants to understand that one will have to read my book, because it's several paragraphs to explain that. Okay. Anyways, it's in my book. It's not that I'm copying out. But what I want you to understand instead is why it's the hydrogen atom and why it's velocity of light squared. Okay, why that's the case, why that gives you the force of gravity, okay, which is what we're looking for here. And there it is, okay, every atom is connected to every atom in the universe by electromagnetic ropes. They torque the rope, and the signal goes in both directions, from one hydrogen atom to all atoms in the universe, and from all atoms in the universe to our test or our hydrogen atom. That's what's happening. So you have light travels in both directions simultaneously, from one atom to every atom, and from every atom to our atom. Okay, and so that gives you an idea why the gravitational constant G contains the hydrogen, the mass of the hydrogen atom, and also the velocity of light squared. Okay, it just means that light travels in 2 directions. Okay, under the rope model, in quantum mechanics, in general relativity, in mathematical physics, and in string theory, light only travels in one direction because it's mediated by photons. What are photons? Well, supposedly they're corpuscles, but they're not even that. They're just a bunch of numbers. They don't have a physical interpretation for light. What they have is numbers. Okay, and so they have all these numbers traveling in one direction only because they look at values. That's all they're looking at. So they're looking at amounts, values, quantities. That's all they're looking at. Here we're saying no, there's a physical entity between any two atoms. It torques the rope. Okay, that's the mediator. And because it torques the rope, light travels in both directions simultaneously. You can prove that to yourself, proof, evidence. By taking a rope and just twirling it any direction you want, you'll see that the signal really travels in both directions. Both atoms receive a signal. It's a round trip for both, okay? And what is it from one hydrogen atom to another hydrogen atom? That's why you have to have the mass of the hydrogen atom, which has been measured to negative 27 range. So that gives you an idea of what the gravitational constant represents from a physical point of view. And the remaining 0.44 meter per kilogram, that's take it as homework.